So you want to solve some problems. Let's get started. So we're going to be solving problems related to Coulomb's law. And these are going to be calculations. So I have my handy old school calculator, which I'm sure I found somewhere. As it's in front of me. And I'll use that to give you numerical values. Often in physics, problems with numerical values are given to starting students because they're more familiar with plugging numbers in. But in general, the proportionality video from earlier may give you a better sense of how things are related. Not a huge fan of numbers myself. I prefer working with variables, but we're going to try out some examples today. Okay. So the first example that we're going to use, and remember this is all related to Coulomb's law, F equals K Q1 Q2 over R squared, where K equals 9.0 times 10 to the 9th, that's 9 billion, Newton meters squared over Coulomb squared. And the whole reason that unit is there is so that in the end, when we multiply all this out, we get newtons. Let's have a look at two different situations. The first is where we find the force, which is easy. We're just plugging things into the right side. And then two, maybe we find the distance between things, or the R value. And that's not particularly hard, but it's certainly more complex. Okay. So I'm going to choose a few numbers for our example problems. Okay. For problem 1, and with any problem, you might list your values out in a nice orderly fashion to help you out. I'm going to say that Q1, and I'm just pulling this out of my head, Q1 is going to be 0.0001 coulombs. And then Q2 is going to be 0.0005 coulombs. And the important thing to note is these are both positive. And they're both positive, which means that Q1 and Q2 are positively charged objects. Now I'll say that the distance between them is 0.5 meters. So this distance between these is about a little more than 1.5 feet, 0.5 meters. And this one may have the 0.0001 coulombs, and this one might be 0.00005 coulombs. And so this would be, 500 microcoulombs or something like that. And then this one would be 100 microcoulombs, which are reasonably large charges here. And you'll see why, because we multiply by 10 to the 9th. Now we're at half a meter away, and we'll get some values there. Now we know that K from above is 9.0 times 10 to the 9th Newton meters squared over Coulomb squared. And now to find the force, all we have to do is plug our values in. So we have 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. And then we're going to multiply that by 0.0001 coulombs for Q1. That's Q1. This is K. For Q2, we have 0.0005 coulombs. And then we're dividing by 0.5 meters squared. That's my R value. Okay, and now there are a few ways we can approach this. The first way is to plug it all into your calculator, which you certainly could do. The second is to maybe take advantage of some exponents. I mean, this is this here, if we want to rewrite it, is 1 times 10 to the negative 4. And this is 5 times 10 to the negative 4. So if we multiply those together, 1 times 10 to the negative 4 times 5 times 10 to the negative 4, well, that's equal to 5 times 10 to the negative 8. And on the bottom, what we have is 0.25. This is 0.25 meters squared, if I square this. So that's 2.5 times 10 to the negative 1. Which means that we have here 5 divided by 2.5 is 2. And this divided by this, well, this is equivalent to saying 1 over 10 to the negative 1 is the same as saying, so 1 over 10 to the negative 1 is the same as saying 10 to the first. So 10 to the negative 8 times 10 to the first is 10 to the negative 7th. So what we have is times 10 to the negative 7th. And we multiply that by the k value, 9 times 10 to the negative 9, which is over here. And what we'll get is 18. And this value is in Coulomb squared. And this value is in meters squared. So this is Coulomb squared over meter squared for a unit, and this is Newton meter squared over Coulomb squared. And so we'll see things cancel out. And so what we get is 18 times 10 to the 10 to the negative 9th times 10 to the negative 7, or 10 to the, or not 10 to the negative 9th, 10 to the 9th. Times 10 to the negative 7th is just 10 squared. So 18 times 10 squared is 18 times 100, which is 1800. And the meter squared cancels with the meter squared down here, and the Coulomb squared cancels with the Coulomb squared here. And so we'll get just newtons as the unit here. Or in scientific notation, 1.8 times 10 to the third newtons. And you should hopefully get the same thing if we plug this into the calculator. We can say 9 times 10 to the 9th times 0.0001 times 0.0005. And then we divide that by 0.25, and we get 1800. Okay, and so you can do it both ways. If you don't have a calculator, you can still do these problems. You just do have to be familiar with exponent rules and be comfortable with some arithmetic. But in general, when you solve these, you'll probably have a calculator around you. Okay, the next one, I'm not really going to mess around with the exponent. Well, I may do that, but it may be quicker. So what we're going to do is we're going to erase a lot of this, and we're going to start with a problem 2. Massive erasure. Oh, don't want to move that. Okay, so now let's look at a new problem. Let's look at a problem where we have to find the distance. So problem 2, what we're going to look at is we're going to say, okay, well, maybe we know that the force is going to be 100 newtons of force. By the way, from our last problem, 1,800 newtons of force is a significant amount of force. I mean, we're looking at like 400 pounds of force there from just 2 charges of that size half a meter away. That tells you that the charge 0.0001 coulombs or 0.0005 coulombs, those are pretty big charges. You're getting a lot of force there. So let's say we have the force be 100 newtons. Let's say my Q1 is 0.005 newtons for 1. And then for Q2, I have 0.00001 newtons. Okay, so we have a proper microcoulomb there. Equals, or not, why am I using newtons? Oh, goodness. So this is coulombs. Coulombs, because the unit for charge is coulombs. Always check your units. Good thing I went back. And so what I have is that's equal to 1 microcoulomb. And this is equal to like 5,000 microcoulombs. We often will write things in microcoulombs, which are millionths of coulombs. And so what I'll get, and I'm writing it this way for ease of calculation, and we know that K is 9.0 times 10 to the negative, or 10 to the 9th, not negative 9, 10 to the 9th Newton meters squared over Coulomb squared. Okay, because again, electrostatic force is a pretty big force. So now we want to say, okay, well, what is R? Well, again, we'll plug in. So this time we plug in for the force, 100 newtons, is equal to 9.0 times 10 to the 9th. I'll leave the units out here and we'll just trust that they work out. Times 0.005 times 0.000001. Oh, that's too many zeros. And then we'll divide that by my R. Now, before I even start this, you could do a bunch of calculation here, R squared. But it might be even easier if you first rearrange your equation. So a rearranged equation would look like this. Okay, so we know that force equals K Q1 Q2 over R squared. But I want R to be the thing I'm finding. So one way to do that is I'll switch these two. And so I get R squared equals K Q1 Q2 over F. And if you feel uncomfortable with that, you can do your algebra. I'll give you an algebra arrow there. With algebra, we get that. And so that the R is equal to the square root of K Q1 Q2 over F. Okay. And note that we should get a positive value under this square root because any negative should balance out between these three things. If these two are negative, the force would be positive. So we have a negative here. If these two are opposites, then the force is negative. And so it'll all balance out to a positive value under the square root. So we have no imaginaries here, imaginary numbers. So I could just write that R equals this and plug things into here and plug into my calculator, or I could be the just plug things in the lazy way, the unthinking way, and get some values and have to do my rearranging later. In fact, I hate that idea so much that I'm just going to write R squared. I'll have R squared be there, and we'll get 9.0 times 10 to the 9th times 0.005 times 0.00001 divided by 100. And if I plug those into my calculator, which again is an extremely slow process, times 10 to the 9th, times 0.005 times 0.51, divided by 100, I get that r squared is equal to 0.45. And the unit here is meters squared. This is newtons. This is newtons times meter squared over Coulomb squared. These are both Coulomb, so we have Coulomb squared on the top. Those cancel, newtons cancel, we're left with meters squared. Please try that out yourself. It's a good exercise. And then therefore R is equal to root of 0.45 meters squared, which is 0.67, based on our significant figures, 0.67, although I'm not sure I was proper with that. 0.67, and what's the unit here? It's meters. Okay, or if I wanted to use proper significant figures, 0.7 meters, since I only know these to one significant figure. And I know this to one significant figure, and I know this to two. Okay, so this is the distance that they'd be apart under these conditions. They'd have to be this far apart to produce 100 newtons of force. I could go back and choose a force for my first problem and then figure out how far apart that would be, those would be, but that's where we're at right now. Okay, keep in mind that the signs matter here, and you should include them. If you have negatives or positives, please include them. Okay, I'm going to cut it for now, and I guess it's time to sleep and recharge.